Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. In this module, we are going to look at how can we construct structures which can guide electromagnetic waves from one point to another point. Now, we have already seen such structures. Okay. The first structure is the one that has no structure at all, meaning that it was a free space. So, in the free space, if somehow we were able to generate the electric and magnetic fields whose electric field say is along x direction and whose magnetic field is along the y direction, then this would be the electric and magnetic field picture that you would see. These are the electric field lines and these are the magnetic field lines, and these lines are kind of cross or perpendicular to each other, and this pattern essentially propagates through the free space or a medium which is homogeneous filled with dielectric of some permittivity epsilon r, and the corresponding expression in terms of the propagation was given by something like e power j omega t, where omega is the frequency of this sinusoidal wave times beta z. Okay. And the amplitude was essentially constant. So, if for example, we are writing the electric field was a function only of the propagation direction z and time as well, and it actually had a constant vector E0, and this constant vector, if it is directed along the x axis that we have chosen, then this we would have called as the x polarized plane wave. If it was y, we would have called as a y polarized plane wave, and then the corresponding expression for h also we have written, right. And what is that we have observed is that these waves are also going from point A to point B. They do carry a Poynting vector S, which is given by E cross H in the instantaneous case, or half real part of E cross H conjugate when you convert all the quantities in terms of the phasors, right. So, in some sense, the pattern that you have seen, the x and y lines that you see here, this cross pattern that you see can be thought of as the mode, and this mode which satisfies Maxwell's equations as well as the boundary conditions. Well, in this case there are no boundaries, so the only condition that you are satisfying is the Maxwell's equation, and any such pattern which would satisfy Maxwell's equation and if there are boundary conditions can be called as a mode. Therefore, please take this as a takeaway of this whatever that we have been discussing over the last few modules, is that plane waves can be considered as modes of the free space media or a homogeneous media. Okay. So, that was free space. Unfortunately, the problem with free space is that the wave amplitude, first of all, they are not mathematically, well, mathematically they are possible, but physically they are not possible, because that would require the energy to be very high, right. I mean, it would actually be infinity, because you can imagine a cross section which would extend all the way from minus infinity to plus infinity, a square in the xy plane, and then you would see that electric field and magnetic field and the corresponding S will be a constant in that entire space, and the overall power that you are going to get or energy that you are going to get when you integrate the Poynting vector would be it would actually go to infinity, because you can extend the area. So, moreover, these free space or sorry, the uniform plane waves that we have taken do not have a focusing kind of a property. Like if for example, how do I receive such uniform plane waves? I mean, I can put up my receiver in some way. We are going to talk about what kind of receivers we need to use, but there is no focus. I mean, this receiver is no more special than a receiver that would be put at another position, right. So, because of this, they are not really being guided, more so they are kind of flowing. Okay. So, yes, free space is also guiding waves, but in this sense the word guide is not very tightly defined for the free space waves. We then found out a different kind of a structure, in that at least in the integrated optical circuits, what we found was that if you take a slab of some permittivity epsilon 1 and refractive index n1, and then surround this slab of materials which have permittivity or refractive index n2 less than n1, and in this case n3 also less than n1, then it is possible for us to have guided waves which would propagate, right. And if you assume for a minute that you are looking at the electric field component of this one without bothering whether we are dealing with the TE or TM modes, then this electric field actually had some function of x, correct, because I am assuming that this direction is along x direction and this direction is along z direction. So, the waves should propagate along z. So, in terms of the phasor, we had this e power minus j beta z and this function f of x, right, and different type of functions were present. So, one example for the symmetry case that we saw was that in between you had, that is in the slab you had a nice cosine wave, sorry, or a cosine wave, right. This is the center of the slab that I have taken, that is this particular line, and then outside you had actually this exponentially tapering off or exponentially decaying fields, right. You could of course have a sine kind of a variation as well. So, this was another mode that would also decay out, and you could have more such kind of decaying and that such kind of variations within the slab. So, these are all corresponding to different sine and cosine functions oscillating with respect to whatever the kx oscillation corresponding to the kx value of these fields. But it is important to distinguish that these are not plane waves, which is very obvious, right. You look at these two expressions, although we have not specified the form of f of x, I told you that these are trigonometric cosine and sine functions. Such a function is absent in this E0, right. So, which clearly indicates that although in terms of the phasor the propagation part along z is the same for both types of modes, this particular mode is more confined in the slab, and the outside of this particular slab the energy basically decays rapidly in an exponential form, and this is kind of matches with our expectation of how a mode or a wave would be guided inside a material, right. So, you can imagine that I actually have this kind of a slab, okay. So, this is the slab that I have, and then this is the z axis. So, the mode which would essentially look something like this and exponentially decaying would actually propagate along this particular direction. So, the mode is actually propagating from one point to another point, it would be propagating along this z direction, okay. So, this was one type of a structure. We also saw another structure, although we did not discuss in too great detail because the equations were going to be very complicated, but we also saw that this structure, which is called as an optical fiber, works basically on the same principle that you have N1 less than N1 in the core and then N2 in the cladding being less than less than the refractive index of the core. And then again the solutions were slightly different. They were not really f of x, but they were kind of Bessel functions of appropriate order, right. So, some j nu of r, where r is the radial distance along the center, right. So, in the fundamental case which we said in the weak guiding approximation, you are going to get something called as linearly polarized modes. In this case you had LP01 or LP11, these are the different orders of the modes, and the mode structure was getting more and more complicated, right. In fact, the basic difference between this integrated optical structure that we saw and this one is not only that you have the mode function which is different from the previous mode functions like f of x becoming j nu of r. The point with this with this optical fiber is that you not only have the x component, or in general you have all the three components E r, E phi and E z. In the weak guiding approximation you can have only E r and E phi, but there will be a very weak E z or weak H z depending on which mode that you are looking at. So, in general the two solutions of an optical fiber will have all 6 non-zero components E r, E phi, H r, H phi, E z and H z, but in the weakly guided approximation you can say that E z and H z are kind of very weak compared to the transverse components E r and E phi, H r and H phi. And because r and phi plane can be equally talked about in terms of x and y, can be converted into x and y plane, we normally talk about Ex and Ey and Ez. Ez is in terms of magnitude very small compared to Ex and Ey, okay. But the point is these two had a certain mode structure. These modes are essentially those electromagnetic solutions or solutions of the electromagnetic equations would satisfy Maxwell's equations, and in addition they would also satisfy the boundary condition. In this case you have a boundary at r equal to a core and another boundary which we taken it to be quite far away from the core itself. So, what I am trying to get to you is that when we say a mode, there is only two conditions that a mode has to satisfy. One is Maxwell's equation, okay. These have to be satisfied by all modes. Obviously, otherwise if you have electric and magnetic fields which are not satisfying Maxwell's equations, then they are not true solutions of the electromagnetic field model. So, clearly that cannot happen, at least to our situation that we have considered. And then we have to satisfy the boundary condition. These waves have to satisfy appropriate boundary conditions, and depending on the type of a geometry, the boundary conditions will also slightly be will result in components which are different from one component. So, for example, in the planar slab case, the mode condition was sinusoidal, or the boundary conditions were on a plane, and therefore, the solutions that you get f of x were all trigonometric functions. But when it comes to an optical fiber, the structure is cylindrical, so the corresponding variables have to be used. In between this, we have also seen one more structure. In fact, we started the course with this structure, okay, and that structure happens to be the transmission line, right. We have not really looked at the electromagnetic analysis of this transmission line, but suffice to say that transmission lines are essentially carrying this free space type, the uniform plane wave types. Okay. If you, instead of working with the voltage and the current, you work with the electric field and the magnetic field, you will see that the wave structure that would be present on this transmission line will have the same characteristic in some sense. So, your electric field lines will be directed from top to bottom, and the magnetic field lines will be curling around the top structure. So, it would be curling around in this manner, it would be curling here, and it would be curling in the opposite direction, and you can actually show that you can have a one-to-one relationship between free space and the transmission line structures. In fact, we will look at the electromagnetic analysis of transmission lines as a special lecture in some other the end of the module, where we will also look at the equivalence of describing transmission lines in terms of voltages and currents, or in terms of electric and magnetic fields. So, these are all the different structures that we have seen, although the first one is really not a structure. But what is interesting about these structures is that they do guide waves, okay. Whether they will be completely confined or partially confined, they are all different things. The important point here is that they are not operating at the same frequency, okay. They can be made to operate the same frequency, but the dimensions required will be very impractical. For example, you can have a dielectric waveguide which would be operating at say 1 kilohertz, okay. In that case, the core width that you have to have will be in a few kilometers, right. You have to construct an entire slab of a few hundreds of meters to a kilometer thick, so that the electromagnetic waves at 1 kilohertz can propagate. Okay. The reason for that will become clear when we talk of diffraction in some other module after a few modules here, but that is essentially the point. The higher the frequency, it is kind of easier to squeeze the modes in, and that is why these integrated optical frequencies work very well at terahertz, where the core widths can be just about 2 to 3 micrometers and surrounded by, of course, the cladding of appropriate width, whereas these optical fibers will operate also at terahertz or tens of terahertz, whereas their core diameters will be somewhere around 8 to 50 micron. Okay. So, 8 for the single mode fiber and 50 for the multi-mode fibers. So, these structures, on the other hand, the transmission line structures are good maybe up to about say 2 gigahertz or maybe up to say 10 gigahertz, but again transmission lines are not just a pair of wires, because a pair of wires are good at low frequencies, but as you get to higher frequencies, you for example have to look at this micro strip line, as we have already talked about, right. So, you do have different structures which are tailored for different frequencies, simply because some structures are useful in squeezing the modes at those frequencies, whereas if you try to make the same structure for other frequencies, then the required geometrical parameters will be so huge that it would be impossible or impractical to build such. Okay. So, this is all guided waves that we have looked at. Now, we are going to introduce a different waveguide. Okay. In fact, this waveguide is very similar to transmission line structure that we have looked at. So, in some sense we are doing a transmission line analysis, but then this is not a line, but this is a plane. Okay. The basic idea here is that I am going to introduce the basic idea. So, we are going to look at, so let me, before I go to that one, let me also tell you that the confinement mechanism in these integrated optical waveguides as well as the optical fibers was what we called as total internal reflection. Okay. Whereas the confinement or the guided waves in these transmission line structures, the waves themselves are called as stem waves, and sometimes these lines are called as stem lines. There is the confinement actually, or the guiding actually comes from the two wires that we have actually taken. Okay. And these wires are of course made out of metals. So, there is really no total internal reflection happening, it is a pure reflection phenomena that is happening, which we will look at it in this slide or in this module now. Imagine that you have two planes, okay. These planes actually are assumed to be wide in the x and y directions. Let me get the coordinate system right. So, I am going to assume that this direction is along the z direction, this direction is the x direction, and we will assume this one to be at x equal to plus a and x equal to minus a. So, I am actually putting two planes here. So, you just imagine that these two are two planes, and then the horizontal distance, that is along this way, will be the z direction, and if you look from the top, it would look like a big square, and the square we will assume it to extend all the way from x from minus infinity to plus infinity and y from minus infinity to plus infinity. Okay. However, because you have considered two such planes, there is a discontinuity in the x direction. So, that is, as you go, you will not see a plate, then you will see a plate, then you go no plate, then you will see a plate, and then again you will go and see a plate. However, on the y axis, if you move, you will only be seeing the plane, like you will be seeing only the plate essentially. So, these structures are called as parallel plate waveguides for very obvious reasons, that there are two plates and these plates are actually kept in parallel with each other. The distance between these two plates, I have taken it to be 2a. It is conventional to take the distance as d, but I just wanted to put a symmetry around these two plates. So, I just took them as x equal to a and x equal to minus a. Okay. Now I want to analyze the mode functions or modes of this particular waveguide. I will assume that the lower this one can be neglected, right, that is the lower plate I am removing this, okay, and instead I will imagine that light has been incident, okay. I will incident at an angle of say theta 1, and this is the electric field component say E1, which I have written, or sorry, this is the direction of propagation, which we will write it as K1, okay. So, this is K1, and there will be an electric field component associated with this, okay. These plates are essentially perfect electric conductors, which means their sigma goes off to infinity, okay, and you have this K1 as a direction. Now, you have to obviously ask me, or ask pause the video and then think about a little bit, what way should I put the electric field in, because I know that obliquely incident waves, electromagnetic waves can be either TE polarized or TM polarized with respect to the plane that we are considering. So, I will have to pick something out. I am going to assume that the electric field is actually along the y direction, okay. So, making transverse electric to be the case that I am considering. This has been done just to simplify some of the steps. However, I would encourage and strongly urge you to actually carry out a similar analysis using TM equations as well, okay. But for now we will look at only TE case and get the basic ideas behind what kind of mode functions I am going to get, okay. Now, this light has been incident, this electromagnetic wave has been incident at an angle theta 1 with K1. What would be K1? K1 in this case is obviously given by K1 cos theta along x direction plus K1 sin theta or theta 1 here along the z direction, right. So, this is the K1 vector that we have. Now, you have a perfect electric conductor. What should happen to this wave as it strikes a perfect electric conductor? It is a metal, right. So, metals will not absorb light, and this is a perfectly electric conductor. So, what it actually does is to reflect off this, not light, reflect off this electromagnetic wave at the same angle theta 1, okay. So, the electromagnetic wave is now reflected off, and then reflected wave will also be transverse electric polarized only. So, we can call this as EYR and this one amplitude as EYI, okay, and then this is reflected back. Of course, there will be a magnetic field associated with this one, which you can easily find out, but I am not interested in finding the magnetic field, I am interested in the electric field itself, okay. Far away from the interface, the total electric field in region 1, which I am calling this as the region 1, will actually be equal to the incident electric field and the reflected electric field, correct. So, EYI and EYR. What would be the incident electric field? This is basically some amplitude which we will call as some E0, or let us say we will call this as E0I, and then you have e power minus j k1 dot r plus E0r e power minus j K2 dot R, right. All of this is actually along the y direction, therefore, I can take the y as a common factor out. Okay. Now, what is K2? You can see that the direction of K2 is such a way that it is moving away from the x direction, right. And when you decompose this K2 in terms of its x and y components, you will see that along z it would still remain the same. So, it would be still K1 sin theta 1 z. Can you tell me why K1 is equal to K2? Think about it. Okay. However, on the x1 it would be minus K1 cos theta 1 x hat. Okay. Your r vector of course is given by x hat plus y hat, sorry, z hat, which basically describes any point in this plane. Okay. So, that is your position vector r. Now, what is the boundary condition that we have on a perfect electric conductor? The tangential component must be equal to 0, right. So, the total tangential component on the boundary must be equal to 0, which means that at x equal to 0, and we also know that for the phase factors z at any point of z we should have the same condition, that of course will give you the Snell's law and other things. What this essentially implies is that the reflected EOR amplitude should be equal to minus EOI. Okay. Because you set this one equal to 0 and ask this equation to be equal to 0 for all values of x and for all values of z, you will essentially get that EOR is equal to minus EOI, right. With that, the total electric field in region 1, I can rewrite it as EOI is a common, I will pull this out, and then you have e power minus j k. So, let me call this k1 cos theta as kx and k1 sin theta as kz. Okay. These are two auxiliary variables that I have introduced, which are related to the original k vector as well as the angle of incidence theta 1. Okay. So, I can write this as e power minus j kx x, e power minus j kz z minus EOI, right, e to the power plus j k x x. Please note that along x now k is in a minus x kind of a thing, and then for z it would be e power minus j k z z. Okay. And instead of writing k z, we will go back to our original notation for propagation constant along z, and we will call this as beta. Okay. So, you have EOI, which is the amplitude, times e power minus j k x x minus e power plus j k x x multiplied by e power minus j beta z, which would essentially be present all the time. So, this is clearly showing you that there is some function of x that is getting multiplied with e power minus j beta z, which will describe the total electric field in the region away from that plate, and that starts to look very similar to what we had done for the slab waveguides, except that there are no waves outside this perfect electric conductor, because there is no evanescent wave, at least not what we are considering. We are assuming perfect electric conductor. So, there are no evanescent waves outside, or we will assume that the evanescent waves, even if they are present, they have died down so rapidly that you do not even have to go beyond a few nanometers of or few angstroms above this perfect electric conductor region, that you will actually see anything of that decaying sort of a thing. So, it is a perfect electric conductor, light is incident at an angle, it gets reflected. Instead of light, I am talking about electromagnetic wave, which are essentially same, gets reflected, and when you move away from the interface, at some point when you look at the total electric field, the total electric field will be something like f of x, but it would be propagating, right, along the z direction, right. What is this f of x? Let us look at it. See, you have e power minus j k x x minus e power plus j k x x. So, if you use the trigonometric identities, you are going to get this as minus 2j EOI sin kxx, right, and then you have e power minus j beta z. So, this is the total electric field in region 1, and if you now plot this total electric field in region 1, okay, the magnitude of this one, what you will actually see is that here we had this plate, correct, and this plate was kept at x equal to a, and obviously at x equal to 0, sorry, we kept this one at x equal to a, right, sorry, hold on. We will keep this plate at x equal to 0 initially, sorry to about saying that. So, I will keep the plate at x equal to 0, the rest of the equations will not change, I mean there is nothing that is changed at this point, but we will just take this x equal to 0 to begin with. So, yeah, in that sense I am not really creating a symmetry, but the equations will not change, nothing has changed so far, only even the boundary conditions hasn't changed, right. In fact, we used x equal to 0 as a boundary condition, but I forgot to tell you that. Okay. So, nothing has changed, you simply have the plate coordinate moved at x equal to 0, and now when you plot the magnitude of this electric field, what you would find is very interesting. At some z you have to take, of course, because it keeps changing along z, but some z, this term will be equal to 1, the magnitude if you take, and what you get is the magnitude of sin kx x. Now, let us sketch that. At x equal to 0, sin will be 0, and then it will reach a maximum at some point, and then it will again reach a maxima, and then it would actually go back in this particular manner. You can clearly see that this is beginning to look like a reflection from a short circuited transmission line, if you think of the transmission line still. Of course, you do not have to think in that way. If it is just a plate that has been kept, then you simply have the waves which are moving in this direction, and at the points where you see the total electric field going to 0, it is because of the destructive interference between the forward going wave EOI e power minus j k1 dot r and the reflected wave which is EOR e power minus j k2 dot r, right. Of course, k2 magnitude is equal to k1 magnitude in this particular case. Now, let us do a clever thing. I have this plate already. What if I go and insert another plate at this point where the field is actually going to 0? Where does the field go to 0? Well, it is a sine point where it is going to 0, right. So, where does sin kx of x go to 0? It will go to 0 at all those planes which would actually satisfy this condition, that is at all planes of x such that kx times x is equal to n pi, where n is a number, it is an integer for us, then this field will go to 0. So, the first time that it goes to 0 at this point is x equal to 0, and where does it go to 0 again? It would go to 0 again at say x equals, let us take n equal to 1, because if I take n equal to 0, I do not have any solution here. So, with n equal to 1 as the first solution that is possible, next point where it goes to 0 is when x is equal to pi by kx. But what is pi? What is kx? Kx is basically pi divided by k1 cos theta, right, which actually means, or we will call this entire thing pi by k1 cos theta, and sorry, it is cos theta 1 as a. Okay. So, I will call this one as x equal to a, where a is of course given by this particular expression. Okay. So, whatever that x value which satisfies this equation for a given value of theta 1 and for a given value of k1, we will call it as a, and we have put in a second plate at x equal to a, or maybe we can put the plate at x equal to minus a, because I took this as a positive x direction, but it is really immaterial whether you put it at plus a or minus a, you just have to change n from being positive 1 to minus 1, it does not really matter at all. Okay. The condition that is necessary is that kx times x should essentially give rise to n pi total phase shift, where n could be any integer, but the first such instant that we would have would be when n is equal to 1, and this is the equation that you get. Okay. Let us simplify this equation slightly in terms of theta 1. Suppose in practice what happens is I will be given some x equal to 0 and x equal to a, and then asked to find those values of theta where the electric field can actually go to 0, right. So, I will rearrange the equation to make it cos theta 1 is equal to pi by k1 times a, and k1 being the wave vector, I can rewrite this as 2 pi by lambda times a, and then I can cancel lambda pi from both sides, and then you have lambda by 2a, right. So, the first time when you are going to get the angle of incidence theta 1 for a fixed value of lambda and for a fixed value of a is that. So, if you send in light at that particular instant, the light that gets reflected causes the overall electric field in region 1, right, below the first plate to actually have this periodically going to 0, and this particular insertion of a second plate at x equal to a does not really change anything in terms of the field. The field is automatically satisfying the boundary conditions here. So, the field is automatically satisfying boundary condition, and therefore, this structure can actually be considered as a waveguide. Of course, you can put more such plates, but then things can, you do not want to put more plates because there is no reason to put more plates, right. And the moment you put plates, there will not be any waves in this region as well, okay, because this is also assumed to be a conductor. So, you have automatically satisfied Maxwell's equations by putting two plates at x equal to 0 and x equal to a, and the wave can now begin to move in the z direction just as it would have done in the case of a dielectric planar slab waveguide. with the additional advantage that there are no evanescent fields, at least when your conductivity is very high, there are no evanescent fields outside this particular slab. Okay. This is the, and again in the same way that you have a dielectric waveguide, you will have TE modes, TM modes. The value of n will tell you how many such half cycles you are going to have inside the slab. So, that can be n equal to 1, n equal to 2, n equal to 3 and so on. Of course, n equal to 0 is no point. So, you can skip that particular value of n in this one, and then you have this cos f of x. So, the point here is that you can think of waves propagating inside this metallic or parallel plate waveguide in terms of obliquely incident and reflected waves meeting with respect to each other. So, a picture that is very similar to dielectric slab waveguides, but this picture would work in the range of say about 3 to some 100 gigahertz, not really in the terahertz regions. And these are called as parallel plate waveguides. They are extensively used in a variation of these are used in microwave waveguides. Thank you very much.